everybody. It's Bob Crossan. I'm the Vice President of Content Strategy for the Water and Energy Groups at Endeavor Business Media, a division of Endeavor B2B. I'm joined today by Brian Fincher. He is Product Manager for Separation Technologies for Veolia, and we're going to be talking about DBP removal with high rate clarification while recycling carbon. So, Brian, thank you so much for taking the time to chat with me. I appreciate you being here.
Yeah, thanks for having me, Bob.
Yeah. Why don't we start with kind of the problem first, right? So, DBPs, utilities are feeling challenged by them. What seems to be contributing to that problem then? Why are systems feeling these challenges from DBPs?
So DBPs are a problem, right? It's called disinfection byproducts, and these disinfection byproducts are created when chlorine or another disinfectant reacts with organic matter in the water. And it's becoming a problem in these distribution systems for water plants because we have quite a bit of city and urban growth. And so as these cities begin to expand and people are moving further and further away from city centers, they're also moving further away from their centralized water plants. So our water infrastructure has to not only get longer and larger, and problem with that is that it starts to create issues with retention time in the pipe and the network. So what we see are a lot of these plants are producing water. They're meeting all their regulations. But as the infrastructure gets longer and longer, the retention time within the pipe and network system gets longer and longer. So where you may have had 1 to 2 days of retention time, you're now seeing maybe 2 to 4 days or a week or even
Mm,
longer. And so a lot of these systems are now seeing that they have to sort of change how they're disinfecting the water, right? We have to have the disinfection in order to remove, nasty bacteria, organisms that are harmful. But at the same time, it's sort of creating this other problem in the network. So what we're seeing with the DBPs is that essentially this chlorine disinfectant is reacting with a lot of the organic matter that's just naturally occurring in our raw water. And these DBPs, they create what's called trihalomethanes or THMs or
mm,
haloacetic acids or HAAs. Now, the EPA does set limits on these, just like they set limits on all the constituents in water quality. But what's happening is with these longer pipes and longer networks, we're seeing water plants and systems start to encroach on these limitations. And so what we're trying to do is find ways to reduce the DBPs and the formation of these DBPs. And one way of doing that is essentially going through and treating the organics up front. You know, we're
mhm.
not necessarily trying to get the DBPs out on the back end, but if we can remove the organics up front, we we run a lower risk of having these DBPs form on the back end in our distribution networks. So one thing we can do is to look at reducing our TOCs and our DOCs up front. Um,
Mm.
and one way to enhance that removal is through carbon addition.
Yeah. Yeah. You're talking about that you have this problem that's kind of on the back end of the process, and you could treat it there, but you could also just try and treat it earlier, like you said, here at the front end, and have like this knock-on effect throughout the treatment system that also improves things. But when you're looking at those organics on the front end, where you're trying to deal with that, there, you mentioned carbon there. In addition to carbon, what are some of the solutions that exist? Like how are you guys talking about that with utilities, and what solutions are utilities like gravitating toward? It sounds like carbon being the number one choice.
Yep, carbon is one of the several choices and seems to be the most effective.
Hmm.
But there are other means of removing these organics in the water. So, for example, we'll take a surface water plant, pulls their water from a river or a lake, and they typically have sort of a sedimentation clarification process followed by filtration and then on through disinfection and their clear wells and then onto their distribution network. Within the sedimentation clarification process, typically you see a coagulant used,
Hmm.
and um, you can also have oxidants placed into the water for additional removal, as well as, again, the carbon that we mentioned. So with high rate clarification, you do get a little bit uh, more enhanced removal of these organics as opposed to just the standard sedimentation clarification process. And one of those systems that uses ballast with the high rate clarifier, a ballast is microsand in this case, is the act flow process. And so our traditional act flow process has coagulation, flocculation, or maturation. And in that maturation step, we're adding a polymer that is taking our coagulated particles and our colloidal material, our organics, and attaching it to the sand for the rapid settling. So in that case, that's how we get our smaller footprint. Now, we can also enhance the removal even further by adding powder activated carbon. And by doing that, we actually place a contact tank upstream of the ActiFlow system. We add in the powder activated carbon, and it gets an additional 8 to 10 minutes of retention time in there. So that extra 8 to 10 minutes helps again with more organic removal and more colloidal material as well. So um, by combining all of that together, we get what's called the ActFlow carb process, and we use that, and that can enhance our organics removal and almost double it as opposed to just traditional coagulation alone.
Wow. Yeah. Well, you so mentioned doubling, that doubling being a benefit, and then obviously the footprint being another one. What are some other beneficial things from active flow in this particular instance? It sounds like you already have two big wins already. Is there more to that?
Yeah, so with ActFlow carb process and the powder activated carbon that's in there, you know, we still have a fresh pack dose. And
Hmm.
a lot of times in the typical sedimentation process, a water plant may add carbon or add powder activated carbon, and it's just a single pass. So it gets dosed in the water. You have your retention time through the clarification step, and then it usually settles out with the coagulant material and the flocks that are generated. So with ActiFlow Carb, we still have that fresh pack dose, but
Hmm.
instead of it just being wasted with a single pass, dosed and then waste through a single pass, we actually recycle the carbon back to that pack contact tank. So we're getting a much more efficient use of that carbon and using up more absorption sites within the carbon.
Yeah. Well, that's awesome. Yeah, you can get multiple passes. I imagine that reduces the total carbon you would need to use even. So there's a lot of efficiencies and financial efficiencies even to be had
Yeah,
from a situation like that.
yeah, absolutely. And the fresh pack dose from ActiFlow Carb to a traditional clarifier system, you can reduce that fresh pack dose by almost 33%.
Oh,
So
wow.
it's a pretty significant cost, especially when you start looking at all the chemicals that are used in a water treatment plant. Usually powder activated carbon, if it's needed, is one of the more expensive
Hmm.
products that have to be used. And so if you can reduce that, especially on a larger water plant or water system, it's a pretty significant cost savings.
Yeah. No, well, when I think about carbon too, I often think about PFAS being a part of that equation as well. Often, carbon being such a key tool for dealing with PFAS. I've heard that you guys have seen some potential with active flow carb when it came to the PFAS side of things here too. Would you mind sharing a couple of things that you know currently and what you're hoping to know more about in the future?
Yeah, so the hot topic is PFAS, right? What's commonly known is that carbon is a great source for treating PFAS. And what we found with ActiFlow Carb is with the carbon that we're adding into the system, it has the potential for treating PFAS and the different PFAS compounds.
Hmm.
So one thing to note is that with the carbon, it's not very selective. So it will remove everything that comes in contact with. So in addition to treating PFAS, it can also treat pesticides and taste and odor compounds, pharmaceuticals. There's several things that carbon will absorb onto itself. And what we're finding in pilot testing is that we can treat PFAS, but it really depends on which type of PFAS compounds you have and the different types that are in the water. So what we're finding with the pilot studying is that treating the PFAS compounds with different pack types, whether it's coal-based or wood-based or coconut-based, they each treat different types of PFAS compounds. So to really get down to it, water plants need to know which types of PFAS compounds they have in their water source so that they can treat it with the correct type of carbon. And one thing that we're finding is that we have to look at all these different types of, you know, powder activated carbons to see which ones are
Mhm.
most effective at treating the PFAS and the compounds. So at least for us moving forward, we're still pilot testing and we're still gathering data. Um,
Mhm.
but everything's looking promising and we're starting to see that we're able to treat the PFAS.
Yeah, all the more reason to note just how highly engineered things need to be. You're getting down to actual chemical engineering here of which particular type of carbon is good at treating which particular PFAS chemical. It's
Yes,
fascinating.
it starts to get very tricky and very difficult, and it takes a lot of resources and a lot of time looking at these things.
Hmm. Yeah, and research. So, I
Yeah.
mean, what kind of happens after that? You know, oftentimes you have this spent media. What do utilities need to do with that? Whether they are trying to treat PFAS or maybe it is just DBPs or pesticides, odor, what have you. What comes next? What's that disposal process look like?
So in a typical scenario, a typical water plant, uh, the sludge is usually handled through drying beds or it gets thickened and sent through belt filters or filter presses. And with active flow carb and the carbon that we're using, our our sludge is actually a little bit thicker than normal. It'll come
Hmm.
out around 1 to 3% solids. The volume of sludge generated is actually reduced. So another advantage to active flow carb is that we're only producing zero point 0.1 to 0.3% of the forward flow that's coming through the system. And
Hmm.
that's the amount of volume that we're seeing. And a lot of our installations and with active flow carbs waste, you can just send it off as long as there's no PFAS in it, just normal sludge. You can send it off with your normal coagulated, flocculated sludge to these drying beds and thickeners and belt presses.
Yeah. Well, Brian, thanks so much for chatting with me about this. It's a fascinating conversation about all the different ways that Active Flow Carb can work for a utility. Where can someone learn more about Active Flow Carb if they were interested in getting a better understanding of the technology?
So to learn more about ActiveFlow Carb, you can head over to our website at veoliawatertech.com and you'll find brochures, case studies, more information on how it works and the potential uses for it.
Great. And for everyone who's watching, you can check out our video description below. We'll have that link down there for you so you can easily click and find it. But once more to Brian, thanks so much for taking the time and chatting with me about Active Flow Carb and high rate clarification.
Yeah, thank you, Bob. I appreciate it.